I haven't seen the new one. No. Okay, so this is gonna look really, really straightforward, but this is kind of more of a hey, yay, we can finally do this type piece. F of x is equal to 2x minus 3, a is equal to 2. We want to use the definition of continuity and properties of limits to show that the function is continuous at the given number. So what I can first do is this. We need to use this definition right here. So I'd write this, the limit as x approaches what? 2 of 2x minus 3. Now, can we evaluate that? Why are we allowed to simply plug it in? We can plug it in because if it's a rational function, if it's a polynomial, we can simply just plug it in. That's the rule that works in this situation. So you can go like this. Why? Because it is a polynomial. And those are nice functions that we can simply just plug stuff into. What is 2 times 2 minus 3? 1. Is that equal to f of 2? Yep. So we've said that the limit is equal to the function evaluated at that spot. And we can simply plug it in because it is a polynomial. Is this a polynomial? No, it's a rational function. The same is true though. So we just set it up the same way. The limit as x approaches 1 over x minus 2 is equal to 1 over 1 minus 2, or 1 over negative 1, which is negative 1, which is f, I'm sorry, not f, but g of 1. Why can we do that? Rational function. I'm not going to waste our time on homework by doing those problems. I think you guys understand exactly. We could look at a little bit more difficult problems but it enters kind of a proof realm that I don't think we really need to go through. You guys have done your proofs in section 2.4 proving that the limit exists. We're not going to try to prove continuity as much as we need to. Yes. If a was 2, we would definitely have what we would call discontinuous point at that spot. And so it is not continuous at 2. It is discontinuous at 2. You can't plug it. This is a rational function, but you can't plug in 2 because you would get 0 in the denominator. So it's still a rational function, but it's discontinuous at 2. Good question. Okay. There are 3 types of discontinuities. You have removable discontinuities. Those are the best. Removable discontinuities are what make calculus possible. And you'll see that possibly Monday. We'll see. So again, remember, as we look at the course as a whole, we're talking about limits right now, aren't we? We're talking about limits because we're talking about Q approaching P to find the slope of a tangent line. So we're going to get back to that whole tangent line piece here not too long. But that's why we're investigating limits and continuity and stuff like that. The second type of discontinuity is called a jump. And the third type of discontinuity is called an infinite discontinuity. Okay? What's that? Yep, vertical asymptotes. Exactly. So we'll see 2 of them here. The last one I think will be obvious to you, but we're just going to finish off this page and you have your assignment. It says explain why the function is discontinuous at the given number a. Here I didn't define a. We'll say a is equal to 0 over here. And it says sketch the graph of the function. Well, sometimes what you could do, do you know what x squared minus 4 over x minus 2 looks like? Solvay? Yep, Solvay and MSC, it's trying to look like x plus 2. Here's what they did. They said f of x is equal to x plus 2 times x minus 2 over x minus 2. So this is a function that wants to look like x plus 2. It has what we call a removable discontinuity. Because we can factor it and take it out. We can see what the function wants to be. What does the graph of x plus 2 look like? Good. And so I can draw that function, that line, and when I get to 2, what do I have? An open circle. How did I know the height was 4? I plugged 2 into what it wanted to be like. It wants to be like x plus 2. So I just plug in 2, and you can see it would be at 4, and it goes on from there. So if you have a function that has a hole in it, that's what we call a removable discontinuity. And the idea of a removable discontinuity is that the limit exists in those situations. We know exactly what the limit is. And so therefore we like it. We know a lot about it. It's not that big of a deal to us to have that little discontinuous portion there. And that's super important as we move on to calculus. So it says, sketch the graph of the function. We did. Explain why it's discontinuous. We did. It's removable. Now, here's the third thing I would like you to do, though. I would like you to identify which of the 3 this fails to meet. Does it fail to meet 1, 2, or 3? Does f of a not exist? Does the limit not exist? Or do they not equal each other? F of a does not exist. You can't plug in 2 and get a value. Right? You plug in 2, it's undefined. So removable discontinuity, but it fails, number 1. You could say, I guess. Fails number 1 of the requirements. Yes, you have to memorize requirements for your test. If I don't put some of that stuff on there, it'll be way too easy. So, yep. I think the last test you guys scored high enough on. So, all right, B, f of x is x plus 1 and square root of x. What kind of function do we call that? Piecewise. We graph each function over its given domain. Here, x is less than 0, so I graph x plus 1. I'll graph that. Looks like this. Open or close circle at the endpoint. Open circle right there. Square root of x, what does that look like? And open or close circle at the endpoint. Now, which of the 3 is it? Is it removable, jump, or infinite? This is a jump, meaning you have to pick up your pencil to draw it. It doesn't go towards infinity. There's just a little jump that happens. So we call this a jump discontinuity. Zach does high jump. Very good, Larry. Later on, we'll have snack time. All right. So this would be, Emma asked before, this would be an example of an infinite discontinuity. Or if you have something like, that. Okay. If one part of it goes to infinity, it's an infinite discontinuity. Okay. So that's how we describe that. Let's go back to this one, though. Does it fail to meet 1, 2, or 3? Fails to meet 2. Notice, the limit doesn't exist. As you approach 0 from the left, what is the limit? 1. As you approach 0 from the right, what is the limit? 0, and therefore the limit does not exist, so we have what we call fails number 2. Go watch Mean Girls. Sure, I'll play the clip. Can I do? Yeah, Katie Williams' rap. I gotta call her. Gotta get a hold of her. Oh, well, you should tell her to stop by. The following functions have a removable discontinuity for a point A. Looks confusing. Fill the discontinuity by writing a piecewise function. This sounds difficult, but it's really not that bad. Watch. First, remove the discontinuity. F of x is equal to x plus 3 times x minus 3 over x minus 3. Oh, x plus 3. What cancels? What cancels? X plus 3's. So this function wants to look like what? It wants to look like x minus 3. Okay? Oh. Now, boys and girls, what is the only spot? Okay. Whoop, I'm sorry. So, it wants to look like x minus 3. So what we will do is we will write our original function, x squared minus 9. I got ahead of myself there, I'm sorry. Over x plus 3. I'm sorry, you get rid of it. I made a mistake. What value can x not be for that domain? So here's what we do. We restrict the domain. X cannot be negative 3. So now we fill the discontinuity. Okay, so we already removed the discontinuity. Now we're going to fill it by setting what it should be when x is equal to 3. Let's see if you can figure it out. When x is 3, what should the function be equal to? 0. Oh! I'm sorry. Off my game day. We're approaching negative 3. Negative 3. Okay. So, what is the value of your function at this spot? Negative 6. This is what the function wants to be like, so I simply plug the negative 3 into here, and I get my negative 6 value. So it looks like this all the time. If we were to graph this, we would find that hole, that pixel missing on our graph. And we could fill it by just saying when x is equal to negative 3, let's have the value negative 6. Okay? So, let's, I promise I won't make a mistake on this one. So, that's the problem. Yep. So, let's remove the discontinuity here. So, what does the function want to look like? X squared plus x plus 1. That's what it wants to look like. Okay? So, we'll use that to our advantage. So we'll write a new function, g of x is equal to, and we put our original function back in there. For that function, what is the one value that you cannot plug in for x? X can't equal 1 for that. Let us now fill the discontinuity. X equals 1. What would be the value? You plug it into what the function wants to look like, and we get that. And that's it. Boys and girls, here's the problem that everybody has with this assignment. Okay, don't get confused with the directions for 41. Please fill the discontinuity by writing a piecewise function. For 15 through 20, those are the parts where you have to state why it's discontinuous. Okay, so you identify, is it a jump? Is it removable? I don't know how to spell removable. Is it infinite? Okay? So you got to define one of those. You got to tell then, does it fail 1, 2, or 3? Okay? But the toughest part that people have with 15 through 20 is sketching the graph. So don't be surprised if you get to 15 through 20 and come across a couple where you're like, wait a minute, I don't think I have the graph sketched correctly. This is going to test your knowledge of graphs as well as how to sketch piecewise functions. So if you have to use your calculator, use your calculator. Go ahead.